Alright, welcome back everybody. In this video we're going to look at some examples from the Power Series 2 lesson. Now hopefully you've read through the first page of notes here on Theorems 1 and Theorems 2, which basically all those two theorems tell us is that if we have a series that we know, we can generate additional power series by using either differentiation or integration. And to find the power series for the derivative of a power series we already know, all we need to do is take the derivative term by term of the power series that we already know. And then there's some more talk about intervals of convergence and the possibilities that occur there. You see that right here. The fact that the interval of convergence of our new series will be related to the original interval of convergence for the series, where it'll have the same endpoints. The only question will be whether those endpoints are included or excluded in the interval of convergence. So let's go ahead and we'll take a look here at how we can utilize this. First of all, we're trying to find, that scrolled a little late on me, we're trying to find the power series that represents this function right here, f of x equals 1 over the quantity 1 minus x quantity squared. And so we're trying to think, is there a series that we know that if we took the derivative of it or took the integral of it, it would give us this particular series. And the whole idea here is we know the series for 1 over 1 minus x, which is, scroll up a little bit here, which is equal to quantity 1 minus x to the negative 1. So if I take the derivative of quantity 1 minus x to the negative 1, that's equal to negative 1 times 1 minus x to the negative 2 times the derivative of the inside, which is times negative 1. And so this is equal to the quantity 1 minus x to the negative 2, which is the function that we're trying to find a series for. So in order to find the series for this particular function, all I need to do is take the series that I already know for 1 over 1 minus x, and take the derivative of it term by term, and that's going to give me the series for 1 over the quantity 1 minus x quantity squared. So the series for 1 over 1 minus x is 1 plus x squared plus x to the third all the way up to x to the n, and so on and so forth. And now all I'm going to do to get the series for 1 over the quantity 1 minus x squared is take the derivative of this, term by term. The derivative of 1 is 0. The derivative of x is 1. X squared, the derivative of that is 2x. X to the third, the derivative of that is 3x squared. So on and so forth. N times x to the n minus 1. Alright, now one last thing I'm going to do here. I like to match my general term up so that the first term in my series is the 0th term. That's just, you know, a little quirk. I don't know if everybody does that, but that's something that I do. And right now, this general term that I have, if I put 0 in there, it gives me as my 0th term, it gives me 0 times x to the negative 1, which isn't what I have there. But if I put 1 in there, it gives me this first term. And so I'm going to adjust the general term by either adding or subtracting 1 to all occurrences of n. That recenters this series so that this term that I see at the beginning of my series is the 0th term. And so all I need to do that is increase the n's in here by 1. And so I'm going to write my general term as quantity n plus 1 times x to the n. And now if I substitute 0 in here, I indeed get the terms. This is the 0th term, the first term, second term, etc., etc. All right. Now the last part of this question asks, what do you think the interval of convergence should be? The interval of convergence for the original was from -1 to 1. Now, should this be the interval of convergence for this series? We would think that it should be. The only thing we have to entertain is whether or not the endpoints are included, and we can quickly see that they are not included because if I substitute 1 in here for x for each of these terms in the series, it's going to continue to grow without bound. It's going to be the series 1 plus 2 plus 3 plus 4, and each term is getting larger and larger. Same thing happens with the if I put -1 in there, my partial sums don't have a limit that converges, and so this is going to be the interval of convergence for that series. Alright, let's go on to example 2. Find a power series that represents the function f of x equals the natural log of the quantity 1 plus x. What do you think the interval of convergence should be? Okay, so now I'm looking at a series that I can either take the derivative or integral of that I already know, a common series, that would lead to the function natural log of the quantity 1 plus x. Well, I know the series for 1 over the quantity 1 plus x. And if I take the integral of the function 1 over 1 plus x, I get natural log the quantity 1 plus x. So all I need to do to get my series for this is take the series that I had and integrate each term by term. X minus x squared over 2 plus x to the third over 3 minus x to the fourth over 4 Sorry, I'm having a whole lot of trouble with styluses right now. And then this term is going to be -1 to the n, x to the n plus 1 over n plus 1. And now I want to just check my center, or check out and make sure that this, I shouldn't say check my center. What I should say is check my nth term and see if it generates the terms that I want. If I put 0 in here, that gives me the alternator is positive, and it gives me x to the first over 1. So this is indeed the 0th term of this series. And so there's my series for natural log of the quantity 1 plus x. Now, as far as the interval of convergence goes, the interval of convergence for the original was from -1 to 1, excluding the endpoints. Now, let's think about whether these endpoints are going to be included or excluded here. If we put -1 into this function, we get the natural log of 0, which is undefined. It approaches negative infinity. And so I know I don't need to include this endpoint because it's impossible for me to, get it to converge at that point when this approaches negative infinity. Now, at +1, the question is, does this converge? And that question really comes down to, is the natural log of 2 equal to 1 minus 1/2 plus 1/3 minus 1/4, etc., etc. And there's the natural log of 2. And if we start spitting out some partial sums here, we see that this is dancing back and forth over natural log of 2, getting a little bit closer, with each additional term that we add on. And so I think, at this point in time, I'm not willing to say that for sure right now, but the evidence points pretty strongly to this endpoint being included. And we're going to talk a whole lot more later on about how we determine intervals of convergence, but that's just a quick kind of intuitive approach to that by looking at the partial sums. I think, at this point in time, that this is going to be the interval of convergence for that series. Alright, that's all we have time for in this video. See you guys next time. We'll look at examples 3 and 4 from this lesson and generating some more power series using various techniques that we've learned thus far. Alright, have a great day. See you next time.